In this video, I want to do an example of Newton's second law in two dimensions, this time with something on an incline. So we have this block of mass m on the frictionless incline that makes a small angle theta with respect to the horizontal. Now you push horizontally on the block with a force whose magnitude is equal to that of the force of gravity on the block. What is the acceleration up the block of the incline? At what angle will it no longer accelerate up? What is the magnitude of the contact force the wedge exerts on the block? Okay, let's start with a picture. So I have this wedge, incline set at an angle theta with respect to the horizontal. There's this block of mass m on it, and I'm pushing on it horizontally. I want to apply Newton's second law to this problem. So first I identify an object, that's going to be my blue block. Next, I need to find all the forces on the object. So I encircle it and see what sort of agents cross that barrier. First, there's gravity, that's the one that doesn't have to be in contact. There's this pushing force, it's a contact force. There's also this force from the wedge, which is also a contact force. It's crossing through the barrier there. We know it's frictionless though, so there is no force tangential to the surface. Therefore, the contact force has to be perpendicular. Now I want to take these to a Freebody diagram. When I have a wedge problem like this, I always set up with two sets of axes on my Freebody diagram. I have one set of axes, the gray one, that's set horizontal and perpendicular to the ground. Then I have another set, the pink ones, that are set horizontal and perpendicular to the incline. The next thing is to identify the angles from the problem to the angles of my axes. So looking at my wedge, I can identify that angle as theta, and that's going to be the same as this angle here. Because of the rules of geometry then, every other angle that I've identified with the curved lines are also equal to theta. And that's going to help me find components of my forces on my axes. On a Freebody diagram, the tail of the force goes on the point representing the object. So I have a pushing force, F, horizontal to the ground off to the left. There's a force due to gravity. It is now straight down. And there's a contact force on the block, and it is perpendicular to the surface of the wedge, so it is going to be pointing along this axis. Next, I need a coordinate system. Since I think it is going to be accelerating up the incline, I'm going to have my x-axis parallel to the incline, and then the y-axis perpendicular to the incline. So my x and y axes are along the pink axes of my Freebody diagram. With all my forces, next up is to apply Newton's second law. So I've brought back my Freebody diagram. Here's my representation of Newton's second law. The sum of all of the vectors is equal to the mass of the object times the acceleration of the object. I like looking at this vertically because it gives me a nice representation of what exactly Newton's second law means, and now I can turn them into scalar equations by looking at the components. Let's look at the pushing force first. Notice that my axes, remember, are the pink ones, so I need to find my components along the pink set of axes. So to find the components, I draw a line from the tip of the vector to one of the axes such that it makes a right angle. Now the magnitude of the force corresponds to the hypotenuse of this triangle. With the magnitude equal to the hypotenuse, the length of the sides of the triangle correspond to the magnitudes of the components. And then I look on the graph to determine whether those signs are positive or negative. This helps me a lot to get them right. So first is the x component. That's the length of this blue line. So that's the magnitude times cosine theta. And I note that it's pointing in the positive x direction. The y component is the magnitude sine theta, and I note that this is pointing in the negative y. If it helps, you can actually label your axes. There's plus y, this is negative y, and this is negative x, and this is positive x. The pink axis here is where y is equal to 0, so you can see the orange component is going in the negative y direction. Now on to the force of gravity. Note that the force of gravity is also not along the pink axes, so I need to find its components. I draw a line from the tip of the vector to one of the axes such that it makes a right angle. And now I need to find the sides of that triangle where the magnitude of the force is the hypotenuse. Notice in this case, the x component is the magnitude sine theta. Remember from geometry before, I know that this angle is theta, and the x component is opposite that angle. Also, it is pointing in the negative x direction. The y component is the magnitude times cosine theta, and it is pointing in the negative y direction. The final force is the contact force, only has a component along the positive y direction, so its x component is 0 and the y component is simply the magnitude. Next, I sum these forces is equal to the mass times the acceleration, and so the x component is just the mass times the x component of the acceleration, and the y component is the mass times the y component of the acceleration. Now I can turn Newton's second law, which is a statement about vectors, into scalar equations that I can use to solve my problem. The sum of all the x components is equal to the x component of MA, and the sum of all the y components is equal to the y component of MA. Here's an equation for the x component, and here's the equation for the y components, where I make sure I keep the right signs. So what else do I know about this problem? I know from the gravity model that the magnitude of the force due to gravity is mg. I was told in the problem that's also equal to the magnitude of the pushing force. I also know that the acceleration along the y dimension is 0. That was the reason I set up my coordinates that way in the first place, so I would only have a component of acceleration along the x-axis. Let's substitute this into the blue equation and see what we find. So here I've put in the magnitudes of the pushing force, which is just mg, and the magnitude of the gravitational force, which is also mg, and I get this relationship. It looks like I can cancel my masses, and I've already solved for a. I have a g in each of my terms on this side, so I'm going to factor out that g. And I get a result for the acceleration, which is the acceleration due to gravity times this term cosine theta minus sine theta. So the first step is, does this make sense? Well, it certainly has the right units. These are dimensionless, and this has units of acceleration. When I have angles like this, I always check the limiting cases. Well, at theta is equal to 0, it looks like this. I'm just pushing it across a frictionless surface. What is the acceleration in this case? Well, if theta is equal to 0, sine theta is equal to 0, and cosine theta is equal to 1, and so the acceleration is just g. And that makes sense. Because it's frictionless, the only force on this object in the horizontal dimension is this. It's equal to the force due to gravity, and so we would expect the same acceleration of the object. What happens at theta is equal to 90 degrees? Well, now it looks like this. And what's happening? In this case, sine is equal to 1, cosine is equal to 0, and we've gotten an acceleration of negative g. This also makes sense, because while this force may hold it against the wall is frictionless, so it can't stick there, and nothing is opposing it simply falling under gravity. And since there's nothing opposing gravity, in this case, we should expect an acceleration whose magnitude is equal to g going down, which was in the negative x direction in this case. So you can get an idea of what's happening. At small angles, it's being pushed forward due to the pushing force. But as the angle gets larger and larger, eventually the pushing force isn't sufficient and it starts sliding back down because the component of gravity along the incline is stronger, to the point where you finally get to here where it's just falling. So at some point, the acceleration goes to 0. There's a maximum angle at which you can no longer push it up the incline under these conditions. That was one of the things that we were asked to find. What is that maximum angle? That maximum angle then is when the acceleration goes to 0, or when cosine theta is equal to sine theta. To see this, you could just do a little graph of the acceleration as a function of theta. At theta is equal to 0, it's positive g. At theta is equal to 90 degrees, it's negative g. And so at some point, the acceleration has to go through 0, and that's the maximum angle at which you can push it up the incline. So we can solve that. That's easy enough. That angle where cosine theta is equal to sine theta is 45 degrees. And you know, that makes some sense too, because it's at that point now where the component of gravity becomes larger along that axis, becomes larger than the component of the pushing force along that axis, and the force of gravity takes over, and it starts accelerating back down the incline. So the final step is to find the contact force. And if you recall, there's that orange equation had the contact force in it, and so we can use that to solve. So there's the orange equation where I have substituted in mg for the magnitude of the pushing force, the force due to gravity, and of course the acceleration in the y dimension is equal to 0. And so I can solve now for the magnitude f sub c, which just brings these two terms over to the other side. I think I'd like to factor out a factor of mg, and so the contact force is equal to mg sine theta plus cosine theta. Does this make sense? Well, at theta is equal to 0, sine theta is equal to 0, cosine theta is equal to 1, and the contact force is just equal to mg. And that makes sense because if I look in the y dimension, there's the force due to gravity on the object, there's the contact force on the object, and it's not accelerating in the y dimension, so they have to be equal. What about at theta is equal to 90 degrees? We get exactly the same result because sine theta is equal to 1, cosine theta is equal to 0. So again, the contact force is equal to a positive mg. And that makes sense because now it's only opposing the pushing force. There's a pushing force in that direction, there's a contact force in that direction, and since there is no acceleration in that dimension, the magnitudes have to be equal. So Newton's second law takes the same approach over and over again. Choose an object, find the forces on the object, Freebody diagram, thus vector sum of all the forces is equal to the mass of that object times the acceleration of that object, and then extract scalar relationships and equations to be able to solve for the things that you want to find. Highlighted here are both how to deal with something on an incline where you can tilt the axes so you can have a 0 acceleration in one dimension, as well as making sure that you check limiting cases to gain confidence that you've got the right answer.